Have you ever wondered what the universe looked like in its very first moments? Picture this: a time so ancient, so far beyond our ordinary understanding, that even the stars and galaxies we see today had not yet been born. What if I told you there's a faint, ghostly glow still lingering from that primordial dawn, a whisper of light that has traveled across more than 13 billion years to reach us? This isn't science fiction, it's real. It's called the cosmic microwave background, and it's the oldest light in the universe. Think about that for a second. We're not just talking about distant galaxies or ancient stars, we're talking about a snapshot of the cosmos when it was just a newborn, a mere infant in the grand timeline of existence. And somehow, against all odds, we've learned how to read its secrets. This incredible glow is more than just a scientific curiosity, it's a time machine. By studying it, we've uncovered clues about how the universe began, how it grew, and even what might happen to it in the far, far future. The cosmic microwave background is like the universe's baby picture, etched into the very fabric of space itself. And the stories it tells are nothing short of breathtaking. Did you know, for example, that this light holds tiny temperature variations imperceptible to the naked eye that reveal the seeds of all the galaxies, stars, and planets we see today? Or that it carries echoes of a time when the universe was so hot and dense that atoms couldn't even form? These aren't just abstract ideas, they're pieces of a puzzle that help us understand where we came from and maybe even where we're headed. In this video, we're diving deep into 30 astonishing facts about this ancient light, unraveling its mysteries one revelation at a time. We'll explore how scientists first discovered it almost by accident, how it revolutionized our understanding of the cosmos, and what it tells us about the universe's most fundamental secrets. From the mind-bending physics of the Big Bang to the cutting-edge telescopes scanning the skies today, this is a journey through time, space, and human curiosity itself. So if you've ever looked up at the night sky and felt that tug of wonder, that longing to understand the grand story of existence, you're in the right place. By the end of this video, you'll see the universe in a whole new light. Literally. The cosmic microwave background is the oldest fossil in the universe, a relic from the moment our cosmos first blazed into existence. Think of it like the lingering heat from a campfire long after the flames have died. Only this isn't just any fire. This is the afterglow of the Big Bang itself, a faint whisper of radiation stretching back 13.8 billion years, carrying secrets from the universe's very first breath. Back in 1965, two radio astronomers named Arno Penzias and Robert Wilson made one of the greatest accidental discoveries in science. They were tinkering with a sensitive antenna in New Jersey, trying to eliminate mysterious static interfering with their experiments. No matter how much they tweaked the equipment, the noise wouldn't go away. At first, they even blamed pigeons nesting in the antenna, scrubbing away bird droppings in frustration. But the signal persisted. It wasn't until they crossed paths with physicists studying early universe theories that the truth clicked. That stubborn static wasn't a glitch. It was the echo of creation. What Penzias and Wilson had stumbled upon was the CMB, radiation so ancient it had cooled over billions of years to just a few degrees above absolute zero. This discovery didn't just solve their technical headache, it reshaped cosmology forever. The CMB proved the Big Bang theory wasn't just speculation. Here was tangible evidence of the universe's explosive birth, a smoking gun written in microwaves across the entire sky. Imagine holding a photograph of yourself as a newborn, but instead of a tiny face, it's a grainy image of the cosmos before stars, before galaxies, before anything recognizable even existed. That's what the CMB gives us, a snapshot of the universe when it was just 380,000 years old, so hot and dense that light couldn't travel freely. As space expanded and cooled, that trapped light broke free, stretching into the microwave glow we detect today. every direction we look, this glow surrounds us, a time capsule from the dawn of everything. And here's what's even wilder, those tiny temperature fluctuations in the CMB, no bigger than 1 part in 100,000, weren't random noise. They were the cosmic blueprints for everything we see today. Those microscopic ripples became the gravitational seeds for galaxies, clusters, and the vast cosmic web we observe now. Without them, the universe would have stayed a featureless soup of particles. Instead, they gave rise to the grand structures that define our home in the cosmos. So when you gaze up at the night sky, remember, you're seeing the grown-up version of a story written in light older than time itself. Here's something that might blow your mind. No matter where you are in the universe, if you could tune into the right frequency, you'd find the cosmic microwave background surrounding you like an invisible fog. It doesn't matter if you're floating near a distant quasar, drifting between galaxies, or sitting in your backyard on Earth. This ancient light is everywhere, filling every corner of space with its faint, ghostly glow. You can actually think of it like the static on an old television set, that snowy, grainy noise you'd see when a channel wasn't tuned in properly. Believe it or not, about 1% of that static wasn't just random interference. It was the CMB, subtly whispering its presence into living rooms around the world long before we even knew what it was. That's how pervasive this signal is. Even our everyday technology was accidentally picking up echoes from the birth of the universe. What's truly fascinating is how uniform this glow appears, almost the same temperature no matter which way you look. But almost is the key word here. Those tiny variations, barely detectable, tell an incredible story. They're like cosmic fingerprints, marking where matter was slightly denser or sparser in the early universe. And from those subtle differences, everything we know, galaxies, stars, planets, eventually grew. Imagine standing in a vast, pitch-black room with a single light bulb flickering far in the distance. Now imagine that, instead of darkness, the entire room is filled with a dim, even glow. That's the CMB. It's not coming from one place, it's coming from everywhere at once, a remnant of a time when the universe was too young to have light sources like stars. Instead, space itself was glowing, a searing hot plasma that only cooled into transparency after hundreds of thousands of years. And here's the wild part, because the universe has been expanding for billions of years, that light has stretched. What once was visible light has now shifted into microwaves, far beyond what our eyes can see. But with the right instruments, we can still detect it, like tuning a radio to a station from the dawn of time. That's why astronomers call the CMB the universe's baby picture. It's the oldest light we can observe, and it's literally all around us. Right now, all around you, the oldest light in the universe is silently drifting through space, but it's not what you'd call warm. The cosmic microwave background has chilled to a staggeringly low 2.7 Kelvin. That's just 2.7 degrees above absolute zero, the coldest possible temperature in the universe, or around negative 270.45 degrees Celsius. To put that into perspective, that's colder than the icy void between galaxies, colder than Pluto's frozen surface, even colder than the deepest reaches of space we've ever measured. And yet, this frigid glow is what's left of a universe once so hot it could vaporize atoms in an instant. How did something so blisteringly hot become so cold? The answer lies in the relentless expansion of space itself. Think of it like a steaming cup of coffee left out in winter. Over time, it loses heat to its surroundings. But in the case of the CMB, the surroundings are the ever-stretching fabric of the cosmos. As the universe expanded over billions of years, that primordial light stretched along with it, its waves growing longer and its energy fading. What started as a searing, visible glow gradually redshifted into microwaves, its temperature dropping to the faint whisper we detect today. But here's the twist: while the CMB is incredibly cold, it's not perfectly uniform. If you could measure it with impossibly precise instruments, you'd find tiny variations, fluctuations no larger than 1 part in 100,000. Picture a vast, calm lake where the surface appears perfectly smooth from a distance, but up close you notice ripples subtle, barely there, yet shaping everything beneath. Those minuscule temperature differences in the CMB are like cosmic ripples, the faint imprints of density variations in the early universe. These fluctuations might seem insignificant, but they're cosmic gold. They tell us where matter was slightly denser, where gravity would eventually pull gas and dust together to form the first galaxies. Without those tiny deviations, the universe would have remained a featureless expanse, a monotonous sea of particles with no stars, no planets, no us. That's the paradox of the CMB. It's both a relic of extreme heat and a testament to how cold and structured our universe has become. And here's something even more mind-bending. That 2.7 Kelvin temperature isn't just a random number. It's a direct consequence of the Big Bang's physics, a smoking gun that confirms our universe had a fiery, dense beginning. When scientists first calculated what the CMB's temperature should be based on cosmic expansion, their predictions matched the real measurements almost perfectly. It's as if the universe left us a receipt, a way to check its own history. So the next time you hear about the CMB, remember, it's not just cold, it's a precise cosmic thermometer, one that's been counting down the degrees since the dawn of time. To understand just how revolutionary the cosmic microwave background is, you have to realize what it captures. A moment frozen in time when the universe was only 380,000 years old. That might sound ancient, but in cosmic terms, it's practically newborn. Picture holding a photograph of yourself from your first hours of life, except this image shows the entire cosmos in its infancy, a blurry but breathtaking glimpse of existence before stars, before galaxies, before anything familiar had taken shape. What makes this possible is a pivotal moment called recombination, when the universe finally cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this, space was a thick, opaque fog of charged particles, scattering light in every direction like a cosmic thundercloud. But as temperatures dropped, the fog lifted. Light that had been trapped suddenly broke free, streaming across the universe in all directions. That burst of light is what we now detect as the CMB, a snapshot of the exact moment the universe became transparent. Scientists often compare studying the CMB to listening to an echo in a vast canyon. The sound you hear isn't just noise, it carries information about the shape of the walls, the distance they're from you, even the material they're made of. In the same way, the CMB's subtle variations, those tiny temperature differences, reveal the contours of the early universe. Some patches are slightly warmer, others slightly cooler, and these fluctuations map out where matter was beginning to clump together under gravity's pull. It's like seeing the faint outlines of continents on a map before the ink has fully dried. What's astonishing is how much detail we've extracted from this faint glow. By analyzing these patterns, cosmologists have determined the universe's age, its composition, even its ultimate fate. The CMB tells us that ordinary matter, the stuff of stars and planets, makes up less than 5% of the cosmos. The rest is dark matter and dark energy, mysterious forces we're only beginning to understand. Perhaps most mind-bending of all, the CMB lets us see the universe at its most uniform. Those temperature variations, while crucial, are incredibly slight evidence that the early cosmos was remarkably smooth. That smoothness is itself a puzzle, one that led scientists to propose cosmic inflation, a theory that the universe expanded exponentially in the first fraction of a second after the Big Bang. Without inflation, the CMB's uniformity wouldn't make sense. So in a way, this ancient light isn't just a baby picture, it's also a detective's clue, helping us piece together events that happened even earlier in the universe's first fleeting instants. And here's the beautiful part, every improvement in our technology sharpens that picture. Telescopes like Planck and WMAP have mapped the CMB with stunning precision, turning what was once a blurry impression into a detailed cosmic portrait. With each new observation, we're not just looking back in time, we're refining the story of how everything came to be. At first glance, the cosmic microwave background seems almost boringly uniform, a sea of microwaves so evenly distributed that if you squint, it looks like cosmic wallpaper. But that uniformity is one of its most astonishing features. Across the entire sky, the CMB's temperature varies by less than 1 part in 100,000, meaning if you compared two random patches of the universe the size of the Moon, they differ by just a few millionths of a degree. That's smoother than a freshly polished mirror. This near-perfect uniformity shouldn't be possible. Picture pouring cream into coffee. No matter how carefully you stir, you'll always end up with swirls, pockets of uneven mixing. Yet the early universe, despite its unfathomable scale, somehow achieved a level of smoothness that defies intuition. How? The leading explanation is cosmic inflation, a theory proposing that in the first trillionth of a second after the Big Bang, space itself expanded faster than the speed of light, stretching quantum fluctuations into the subtle density variations we see in the CMB. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, those dots grow farther apart, but their relative positions stay uniform. Inflation did something similar to the universe, magnifying it from subatomic size to something vastly larger in an instant. Before inflation, different regions of space could have been close enough to exchange heat, balancing their temperatures like neighboring cups of coffee on a table. Then inflation stretched those regions apart so abruptly that they were frozen in place, locked into that eerie uniformity we observe today. But here's where it gets even wilder. Without those minuscule imperfections in the CMB, our universe would be unrecognizable. A perfectly uniform cosmos would have remained a featureless void, no galaxies, no stars, just endless sameness. Those tiny fluctuations, imprinted during inflation, became the gravitational seeds for everything we see. Warmer spots marked denser regions where matter would eventually collapse into galaxies. Cooler spots hinted at the voids between them. The CMB's uniformity isn't just a curiosity, it's the canvas on which the entire cosmic story was painted. And inflation isn't just a wild guess. The CMB's patterns match predictions with breathtaking precision, like finding a fingerprint that exactly fits a suspect's hand. For example, inflation explains why the universe appears flat on large scales, another puzzle the CMB helped solve. It's as if the cosmos left us a carefully coded message, and we're only just beginning to decipher its full meaning. Yet mysteries remain. Why did inflation start or stop? Are there other universes beyond ours, each with its own CMB? These questions push the limits of our understanding, but the CMB gives us a starting point, a Rosetta Stone for the universe's earliest moments. So while that microwave glow might seem tranquil, it's really a frozen storm, a relic of the most violent, transformative event in existence, and the key to unlocking how everything began. Those tiny ripples in the cosmic microwave background, almost imperceptible at first glance, hold the secret to why our universe looks the way it does today. Imagine the early cosmos as a vast, quiet pond, its surface nearly flawless except for the faintest disturbances, like raindrops barely touching the water. Those minuscule temperature variations, known as anisotropies, were the universe's first unevenness, the subtle wrinkles that gravity would later amplify into galaxies, clusters, and the sprawling cosmic web. Here's how it happened. In regions where the CMB was slightly warmer, matter was a tiny bit denser. That extra density meant stronger gravitational pull, drawing in nearby particles over millions of years. Like snowballs rolling downhill, these clumps grew larger and more massive, eventually collapsing into the first stars and galaxies. Cooler spots, on the other hand, marked the seeds of cosmic voids, vast, nearly empty expanses where matter had been sparser from the start. What began as fluctuations no larger than 1 part in 100,000 became the blueprint for everything we see when we look up at the night sky. The beauty of this process lies in its simplicity. The same physics that makes an apple fall to the ground, gravity, orchestrated the universe's grand structure, sculpting light years of empty space and glittering galaxies from those primordial whispers. Without those anisotropies, the cosmos would have remained a featureless sea of particles, silent and unchanging. Instead, they became the universe's first architects, their influence stretching across billions of years. Scientists have even mapped these fluctuations with extraordinary precision, revealing patterns that match predictions almost perfectly. The CMB's hottest and coldest spots aren't random. They form intricate, mottled patterns like the pores on a slice of bread or the cracks in dried mud. These patterns tell us not just where galaxies would form, but how they'd cluster together, weaving the cosmic web we observe today. It's as if the universe left us a set of instructions written in the language of microwaves, and we're only now learning to read them. But here's what's truly astonishing: this process wasn't fast. Those initial ripples needed hundreds of millions of years to grow into something recognizable. The first true galaxies didn't emerge until the universe was at least 500 million years old, their light now visible only in the deepest telescopic images. Yet their origins trace back to those fleeting moments just after recombination, when the CMB's fluctuations were frozen into the fabric of space, and the story doesn't end there. Those same structures continue evolving even now, with galaxies colliding, clusters merging, and dark energy stretching the cosmic web ever farther apart. The CMB is more than a relic. It's the opening chapter of an epic that's still unfolding, one where we're not just observers but part of the narrative. Every atom in your body, every star in the sky, exists because of those delicate, ancient imperfections. The universe, it turns out, owes its richness to the tiniest of beginnings. One of the most astonishing things about the cosmic microwave background is how it serves as a cosmic clock, allowing scientists to pin down the age of the universe with jaw-dropping precision. Think about it, we're talking about measuring time on a scale so vast it's almost incomprehensible, yet thanks to the CMB, we can confidently say the universe is 13.8 billion years old, give or take a mere 40 million years. That's like determining the age of a towering ancient tree by examining a single ring with microscopic accuracy. Here's how it works. When we map the CMB's temperature fluctuations and analyze their patterns, we're essentially reading the universe's birth certificate. Those tiny ripples in the microwave glow encode critical information about the cosmos's composition: how much of it is ordinary matter, how much is dark matter, and how much is dark energy. By plugging these numbers into equations based on Einstein's theory of relativity, cosmologists can rewind the expansion of the universe like a cosmic film reel, tracing it back to the moment of the Big Bang. The key lies in the CMB's uniformity and its subtle imperfections. The average temperature, 2.7 Kelvin, tells us how much the universe has cooled since recombination. Meanwhile, the size and distribution of those minute fluctuations reveal how fast space has been expanding over billions of years. It's like examining the cracks in an ancient painting to deduce not just when it was made, but the humidity and temperature of the room where it dried. What's truly mind-blowing is how multiple independent methods converge on the same number. Measurements of distant supernova, the clustering of galaxies, even the decay of radioactive elements in ancient stars. They all align with the age calculated from the CMB. It's as if the universe left us multiple cross-checked receipts, each one confirming the same cosmic timeline. But here's where the CMB stands apart. While other methods rely on observing objects within the universe, stars, galaxies, or exploding supernova, the CMB gives us a direct line to the universe's infancy. It's not just a measurement, it's a time capsule from the moment light first broke free, offering an unobstructed view of the cosmos before any stars or galaxies existed. That's why it's considered the gold standard for cosmic dating, the most reliable yardstick we have for the universe's age, and the implications stretch far beyond mere curiosity. Knowing the universe's age helps us understand its fate. Will it keep expanding forever, collapse back in on itself? The CMB's data suggests the former, painting a picture of a cosmos destined to grow colder and darker as eons pass. But for now, it's enough to marvel that we can peer back over 13 billion years and say with astonishing certainty, this is when it all began. The cosmic microwave background does more than just reveal the universe's age. It holds crucial clues to its hidden ingredients. Buried in those faint temperature fluctuations is evidence of dark matter's invisible grip and dark energy's mysterious push, two forces that shape the cosmos yet remain frustratingly out of sight. Here's how the CMB exposes their presence. Those tiny anisotropies, the warmer and cooler patches, aren't just random blips. Their size and distribution act like a cosmic scale, measuring how much matter exists in the universe and how it clumps together. But there's a catch. When scientists tally up all the visible matter, stars, galaxies, gas, it accounts for less than 5% of what the CMB says should be there. The rest, that's where dark matter enters the picture. The CMB shows that matter's gravitational pull affected how those primordial ripples evolved. Larger fluctuations would have grown more pronounced over time if only ordinary matter existed, but the patterns we see suggest something else was at work. An invisible scaffold of dark matter, 6 times more abundant than normal matter, guiding the formation of cosmic structure without emitting a single photon. Imagine trying to reconstruct a building's blueprint by observing how people move through its halls, even though the walls themselves are transparent. That's what cosmologists did with the CMB, mapping dark matter's shadowy architecture through its gravitational fingerprints. And then there's dark energy. The CMB not only confirms its existence but reveals when this enigmatic force took over the cosmos. By comparing the universe's early expansion rate imprinted in the CMB's fluctuations with its current accelerated growth measured by supernova, scientists found a startling discrepancy. Around 5 billion years ago, dark energy began overpowering gravity's pull, driving galaxies apart faster and faster. The CMB's data perfectly aligns with this cosmic tug-of-war, showing that dark energy makes up nearly 70% of the universe's total energy budget. What's astonishing is how elegantly these pieces fit together. The CMB's patterns act like a Rosetta Stone, translating the universe's composition into numbers we can calculate. Roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. Without this ancient light, we might still be guessing at the cosmos' true makeup. Instead, we have a precise recipe, one that tells us the familiar world of atoms and light is just the faintest shimmer atop a vast, invisible sea of unknown. Yet mysteries linger. The CMB can't tell us what dark matter particles are made of, or why dark energy's strength stays constant over time. These questions push the limits of modern physics, but the cosmic microwave background gives us a starting point. A 13 billion year old message insisting there's far more to the universe than meets the eye. And perhaps that's its greatest gift, not just answers, but an invitation to keep exploring the profound unknowns it so delicately reveals. The cosmic microwave background doesn't just glow, it hums. That's right, the oldest light in the universe carries something extraordinary, an echo of sound waves from the dawn of time. Not sound as we know it, of course. Space is a vacuum and sound can't travel the way it does on Earth. But in the early universe, when matter was still a searing, dense plasma, pressure waves rippled through that hot soup like cosmic drumbeats, leaving faint but detectable imprints in the CMB we observe today. These primordial sound waves, called baryon acoustic oscillations, were born in the universe's first moments. Imagine dropping a pebble into a pond, the ripples spread outward in perfect rings. Now replace the pebble with a burst of energy from the Big Bang, and the pond with an ocean of plasma stretching across the entire cosmos. That's essentially what happened. As the universe expanded, those waves froze in place when matter cooled enough for atoms to form, leaving behind a telltale pattern in the CMB's temperature fluctuations. What makes this so remarkable is how predictable these echoes are. Scientists can calculate exactly how far those pressure waves should have traveled before recombination, a distance of about 500,000 light-years. That measurement became a cosmic ruler, allowing astronomers to gauge the universe's expansion with astonishing precision. When we map the distribution of galaxies today, we find they're slightly more likely to be separated by this exact scale, like faint footprints left by those ancient sound waves billions of years later. But here's where it gets even wilder. The CMB's sound isn't just a single note, it's more like a chord, a mix of harmonics that reveal the universe's composition. By studying these overtones, cosmologists can deduce how much ordinary matter, and dark energy shaped those early oscillations. It's as if the universe composed a symphony in its infancy, and we're just now learning to read the sheet music. And the music isn't silent. Some researchers have even translated the CMB's fluctuations into audible frequencies, creating eerie, otherworldly tones you can actually listen to. The result, a deep, resonant hum, like the lowest note on a pipe organ stretched across light years. It's a haunting reminder that the cosmos isn't just something we see, it's something we might one day hear, a vibration from the dawn of everything. So when you look at a map of the CMB, remember, you're not just seeing light, you're witnessing the fossilized rhythm of a universe finding its voice, a pulse that set the stage for everything that followed. And in those subtle variations, we're listening to the very first sounds of existence itself. The cosmic microwave background we observe today wasn't always microwaves. It began as something far more energetic, a brilliant flash of visible light that's been stretched and faded by the universe's relentless expansion. This transformation, known as redshift, is one of the most fundamental concepts in cosmology, and the CMB offers the most dramatic example of it in action. Picture this: when the CMB first broke free some 380,000 years after the Big Bang, it blazed across the universe as white-hot light, with temperatures around 3000 Kelvin, similar to the glow of a welding torch. But over the next 13.8 billion years, the universe didn't just expand. It dragged that light along with it, stretching its wavelengths like taffy pulled from both ends. What started as visible light gradually shifted into infrared, then microwave wavelengths, cooling to the faint 2.7 Kelvin signal we detect today. Redshift happens because light waves literally stretch as space itself expands beneath them. Imagine drawing a squiggly line on a balloon. As you inflate it, the line grows longer, its peaks and valleys spreading apart. That's exactly what cosmic expansion does to light. The longer the journey, the more stretching occurs, which is why the CMB's redshift is so extreme. After traveling across nearly the entire observable universe, its wavelengths have been stretched by a factor of about 1,100, shifting from the visible spectrum all the way into microwaves. This phenomenon isn't unique to the CMB. We see redshift everywhere in astronomy. Distant galaxies appear redder than they should because their light has been stretched during its journey to us. But the CMB is special because it represents the ultimate limit of redshift, the farthest we can possibly see before the universe becomes opaque. Beyond this point, light couldn't travel freely, making the CMB our final glimpse into the cosmic past. What's astonishing is how perfectly this matches our understanding of cosmic expansion. The amount of redshift observed in the CMB aligns precisely with predictions based on the universe's measured expansion rate. It's like finding a fossil where the layers of rock surrounding it confirm its exact age, except here, the fossil is the entire visible universe and the layers are the stretched wavelengths of ancient light. And redshift isn't just a historical curiosity. It continues affecting the CMB right now as the universe expands faster due to dark energy. In another billion years, the CMB's microwaves will stretch further into radio waves, growing even colder and fainter. One distant day, they'll redshift beyond detectability, erasing this cosmic snapshot entirely. That makes our ability to study the CMB today a fleeting opportunity, a brief window in cosmic time when the universe's oldest light remains just visible enough for us to decode its secrets. So when you hear about the CMB's redshift, remember, it's not just a technical detail about wavelengths. It's evidence of the universe's dynamic nature, stretching and evolving before our eyes, or more accurately, before our telescopes. Those microwaves reaching us now began their journey as dazzling light, only to arrive as a whisper, a faint echo of the universe's fiery birth. Sometimes the greatest discoveries in science happen by pure chance, like when two radio astronomers fiddling with a faulty antenna stumbled upon the universe's oldest light without even realizing it. Back in 1964, Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, trying to eliminate persistent static from a massive horn-shaped antenna designed for satellite communications. No matter what they did, adjusting the equipment, tightening connections, even climbing inside to scrub away layers of pigeon droppings, the annoying hiss remained. It was like trying to tune out a whisper that wouldn't go away, no matter how much you turned the dial. At first, they assumed the noise was some mundane interference, maybe radio waves bouncing off nearby buildings or even the pigeons themselves. But after months of dead ends, they realized this signal was coming from everywhere at once, day and night, in every direction they pointed the antenna. It wasn't just background static, it was something cosmic. Around the same time, a group of physicists led by Robert Dicke at Princeton had been theorizing that if the Big Bang really happened, its afterglow should still be detectable as faint microwave radiation. When Penzias and Wilson heard about this, the pieces clicked. That stubborn noise wasn't a technical glitch, it was the faint echo of the universe's birth. The irony, Penzias and Wilson weren't even looking for the CMB. They weren't cosmologists or theoretical physicists, just engineers trying to solve a practical problem. Their Nobel Prize-winning discovery began as an exercise in frustration, a puzzle they refused to let go of until they'd ruled out every earthly explanation. And that's what makes their story so poetic. The universe revealed one of its deepest secrets, not to someone staring at the stars through a telescope, but to two meticulous tinkerers armed with nothing but a giant metal horn and relentless curiosity. What's even wilder is how close others had come to finding it first. Decades earlier, scientists had theorized about leftover radiation from the Big Bang, but no one had the right tools to detect it. Then, in the 1940s, astrophysicist George Gamow predicted its temperature almost perfectly, yet no one followed up with observations. Even Dicke's team at Princeton was days away from building their own detector when Penzias and Wilson called them, baffled by their mysterious signal. Science is full of near misses, but few are as dramatic as this one, a discovery that rewrote our cosmic origin story, made by accident on the verge of being scooped. The aftermath was just as remarkable. Penzias and Wilson's measurement of the CMB's temperature, about 3.5 Kelvin, aligned almost exactly with Big Bang predictions. It was the smoking gun cosmology needed, silencing lingering doubts about the theory's validity overnight. Their humble antenna, designed for earthly communication, had inadvertently tuned into the oldest broadcast in existence, a message from the dawn of time, waiting 13.8 billion years to be heard. And the kicker, that same faint hiss still fills the air around us today. Every time you hear static on an untuned radio, you're eavesdropping, however faintly, on the birth of the universe. The cosmic microwave background does something extraordinary. It acts like a cosmic carpenter's level, revealing the universe's true shape on the grandest scale. Those subtle temperature fluctuations we've been exploring, they're not just clues about matter and energy, they're also measuring the curvature of space itself. Imagine stretching a bedsheet tight between four posts. If you dropped marbles onto it, they'd roll in straight lines across the flat surface. But if the sheet sagged like a hammock, those marbles would curve inward. If it bulged upward like a saddle, they'd veer outward. The CMB lets us perform this same test with the entire cosmos, using light rays instead of marbles. Here's how it works. In a perfectly flat universe, parallel light beams from the early cosmos would stay parallel forever, like train tracks stretching infinitely without bending. If space had positive curvature like the surface of a globe, those beams would eventually converge. Negative curvature, resembling a saddle shape, would make them diverge. The CMB's patterns serve as our cosmic ruler. By measuring the apparent size of temperature fluctuations across the sky, scientists can determine whether distant light has traveled straight, bent inward, or fanned outward over billions of years. The results were startling. When satellites like WMAP and Planck mapped these fluctuations with exquisite precision, they found the patterns matched a flat universe almost perfectly. Those primordial ripples appear at an angular scale of about 1 degree, exactly what you'd expect if space had no large-scale curvature. This doesn't mean the universe is two-dimensional like our bedsheet analogy, of course. It means that on cosmic scales, the rules of Euclidean geometry hold true. Parallel lines don't meet, and a triangle's angles add up to 180 degrees. But flat doesn't imply boring. This geometry has profound implications. A flat universe suggests the total energy density of everything matter, dark energy, is perfectly balanced at what cosmologists call the critical density. Tilt this balance slightly, and space would curve dramatically over time. The fact that we measure such precise flatness after 13.8 billion years of expansion is no coincidence. It's strong evidence for cosmic inflation, which would have stretched any initial curvature so thin that the universe appears flat to us, much like how Earth's surface feels flat when you're standing on it. There's a beautiful twist here. While the universe appears flat overall, gravity still creates localized warps. Planets, stars, and black holes bend space around them, proving Einstein right on smaller scales. But zoom out far enough, and the cosmos resembles an endless, uncurved sheet. This delicate balance between local wrinkles and global smoothness is why the CMB remains cosmology's ultimate yardstick, a map that doesn't just show us where we are, but tells us what shape the universe calls home. And here's what's truly mind-bending about this flatness. It's not just a static fact. Dark energy's influence means the universe will stay flat as it expands, but the distances between galaxies will grow until they're unreachable. A flat geometry today doesn't guarantee a simple fate. It's the backdrop for an ever more isolated future, where the CMB's light, already stretched thin, will one day redshift into oblivion. For now, though, we're fortunate to live in an era when this ancient glow still holds answers to questions as fundamental as the shape of existence itself. You might think light is just light, but the cosmic microwave background holds a hidden layer of complexity. Beyond its temperature fluctuations, the CMB carries a subtle fingerprint called polarization, a property that tells us how those ancient light waves vibrated as they journeyed through the cosmos. This isn't just some esoteric detail. It's a goldmine of information about the universe's most violent beginnings, including potential echoes of gravitational waves from the first trillionth of a second after the Big Bang. Polarization occurs when light waves oscillate in a preferred direction, like ocean waves rolling parallel to a shoreline rather than caustically in all directions. For the CMB, this polarization emerged during recombination, when free electrons scattered the universe's last uncaptured photons. Imagine a room filled with people holding jump ropes. If everyone shakes their rope randomly, the overall motion is chaotic. But if most ropes start swaying in the same plane, that's polarization. The CMB's polarization pattern split into two types: E modes, which are curl-free and arise from density fluctuations, and B modes, which have a twisting, spiral quality linked to something far more exotic: primordial gravitational waves. Here's where it gets groundbreaking. According to cosmic inflation theory, the universe's exponential expansion in its first moments should have generated ripples in spacetime itself. Gravitational waves powerful enough to leave a faint swirl in the CMB's polarization. Detecting these B modes would be like finding the cosmic equivalent of a dinosaur's footprints, direct evidence of inflation's violent tremors. It's the difference between inferring a storm happened and seeing the actual debris it left behind. The hunt for these B modes has been one of cosmology's most intense pursuits. Telescopes like Bicep and Planck have scrutinized the CMB's polarization with razor-sharp precision, teasing apart signals from interstellar dust that could mimic the sought-after swirls. While definitive proof remains elusive, even the tentative hints have reshaped our understanding of inflation's energy scales. Every new experiment brings us closer to answering whether these gravitational wave imprints are real. And if they are, they'll open a window into physics at energies 1 trillion times beyond what particle colliders can reach. What's astonishing is how much information is packed into these delicate patterns. The CMB's polarization doesn't just trace gravity's earliest ripples. It also reveals how matter clumped together in the early universe and even how fast cosmic structures formed. It's as if the universe encoded its autobiography not just in the light's brightness, but in the very way it dances across the sky. And with each technological leap, we're learning to read deeper into that story, uncovering secrets from a time when reality itself was still taking shape. The cosmic microwave background doesn't just confirm our standard model of cosmology. It serves as the ultimate referee, putting alternate theories of the universe to the test. Take the steady-state model, once a formidable rival to the Big Bang. This elegant idea proposed that the universe had no beginning or end, with new matter continuously created to maintain a constant density as space expanded. A universe without a birth or death, forever unchanging in its large-scale appearance. But the CMB struck a decisive blow against this theory. How could an eternal, unchanging cosmos produce a uniform glow with such precise temperature variations? That faint microwave radiation, along with its intricate fluctuations, pointed unmistakably to a hotter, denser past, a singular origin that steady-state theory simply couldn't explain. Then there's the idea of a cyclic universe, where cosmic expansion and contraction repeat endlessly like a celestial heartbeat. Some versions suggest each cycle leaves traces in the CMB, like echoes of previous cosmic epochs. But when researchers scrutinized the microwave background for anomalies, patterns, or concentric circles that might hint at a pre-Big Bang era, the data held firm. The CMB's fluctuations appear random and Gaussian, just as the standard model predicts, with no clear imprint of earlier cycles. That doesn't entirely rule out cyclic models, but it forces them to explain why no observable scars remain from these hypothetical previous universes. Even more exotic theories like plasma cosmology or modifications to Einstein's gravity must reckon with the CMB's precision measurements. Any viable alternative must account for the exact spectrum of temperature fluctuations, the ratio of dark matter to ordinary matter, and the universe's striking flatness, all imprinted in this ancient light like a cosmic barcode. The fact that the Big Bang model predicts these features so accurately, down to fractions of a degree, makes it extraordinarily difficult for competitors to gain traction without equally compelling evidence. Yet the CMB isn't just a gatekeeper, it's also a catalyst for refining theories. Some researchers propose that slight anomalies in the data, like the infamous cold spot, could hint at physics beyond our standard models. Could these quirks be clues to a multiverse, higher dimensions, or quantum gravity effects? The CMB doesn't just silence rival ideas, it also whispers where our current understanding might need expansion, nudging cosmologists to ask deeper questions. What's remarkable is how this relic light, born in the universe's infancy, continues to shape modern cosmology's most heated debates. It's not merely a static monument to the Big Bang's victory, but a dynamic tool for probing the fringes of our knowledge. Whether confirming long-held theories or challenging bold new ones, the CMB remains the gold standard, a 13-billion-year-old witness that keeps us honest in our quest to unravel the cosmos. The cosmic microwave background isn't just ancient light. It's a portal to a time when the universe was unrecognizable, a seething ocean of particles so dense and hot that not a single star or galaxy had yet formed. Think of it as the ultimate time capsule, buried not in the ground but in the fabric of space itself, waiting 13.8 billion years for us to crack it open. What makes this glow so extraordinary isn't just its age, but the pristine snapshot it preserves, a moment frozen when the cosmos was a mere 380,000 years old, a blink in cosmic terms. To grasp just how primordial this era was, consider this. The universe was 100,000 times smaller than it is today, with temperatures hovering around 3,000 Kelvin, hot enough to vaporize solid metal in an instant. Matter existed as a plasma, a roiling soup of protons, electrons, and photons constantly colliding, scattering light like fog around a street lamp. Yet as the cosmos expanded and cooled, something miraculous happened. Electrons finally latched onto protons, forming the first hydrogen atoms in a process called recombination. Suddenly, light could travel freely for the first time, and that initial burst of liberated photons is what we now detect as the CMB. It's like uncovering a photograph from the universe's first breath, taken before planets, before stars, before even the simplest molecules had a chance to assemble. What's astonishing is how much this ancient glow reveals about conditions we can't observe directly. The CMB's temperature fluctuations act like cosmic weather maps, showing us where matter was slightly denser or sparser in those early moments. These weren't just random variations, they were the seeds of future structure, the gravitational footholds that would eventually pull matter into galaxies and clusters. But the CMB goes even further, preserving clues about events that happened before recombination. The way photons interacted with electrons in that primordial plasma left subtle imprints, like shadows of processes occurring when the universe was just seconds old. Imagine finding a fossilized footprint and realizing it not only tells you the creature's size, but also the temperature of the day it was made, the type of ground it walked on, even the speed it was moving. That's the level of detail the CMB offers. By analyzing its patterns, cosmologists have deduced the universe's composition, confirmed the existence of dark matter, and even glimpsed the fingerprints of cosmic inflation, a theoretical expansion spurt that occurred when the cosmos was less than a trillionth of a second old. And here's the most humbling part. This light has been traveling since long before Earth existed, crossing unimaginable distances only to reach us now. Every photon we detect in the CMB is a messenger from an era when the universe was 1,000,000 times younger than it is today, a time so distant that all of human history is less than a heartbeat in comparison. That's the true power of this cosmic time capsule. It doesn't just show us the past. It connects us to the very origins of everything, a direct line to moments so remote they defy ordinary comprehension. Yet the story doesn't end there. As our telescopes grow more sensitive, we're learning to extract even deeper secrets from this ancient light, from the neutrino background hiding within it to potential hints of exotic physics. The CMB isn't a static relic, it's a living archive, one that continues to surprise us with fresh revelations about how the universe began, what it's made of, and where it might be headed. And the most extraordinary thing, this time capsule isn't locked away in some distant corner of space. It's all around us, bathing the entire cosmos in whispers from the dawn of time. When we look at the cosmic microwave background, the most striking thing isn't just its age, it's the incredible subtlety of its temperature variations. These fluctuations are so tiny they'd be impossible to detect without cutting-edge technology, differing by just 1 part in 100,000. To put that in perspective, imagine standing in a vast desert where the temperature is perfectly uniform except for a single grain of sand that's a fraction of a degree warmer than its neighbors. Now picture that level of precision stretched across the entire sky. That's the CMB's hallmark, an almost eerie smoothness, punctuated by the faintest whispers of variation. But here's the paradox: these minuscule fluctuations are anything but insignificant. They're the cosmic equivalent of a sculptor's faint pencil marks on a block of marble, barely their guidelines that would eventually shape galaxies, clusters, and the vast web of the universe. In regions where the CMB is slightly warmer, matter was a tiny bit denser. Over billions of years, gravity amplified these differences, pulling surrounding gas and dust into those slightly denser patches like cosmic magnets. Cooler spots, meanwhile, became the seeds of today's vast cosmic voids, regions of space nearly empty of matter. What's mind-blowing is how perfectly this process aligns with our understanding of physics. The size and distribution of these fluctuations match predictions based on quantum mechanics. The idea that the early universe wasn't perfectly smooth, but had tiny, random density variations imprinted at the smallest scales. Cosmic inflation then stretched these quantum ripples across the entire cosmos, turning microscopic noise into the gravitational scaffolding for everything we see today. It's as if the universe took the faintest breath of unevenness and over eons exhaled the grand tapestry of galaxies. Scientists measure these fluctuations using a concept called the power spectrum, a graph that shows how common temperature variations are at different angular scales. The peaks and valleys in this spectrum aren't random. They reveal precise details about the universe's composition, from the amount of ordinary matter to the influence of dark energy. The first peak, for example, confirms the universe's flat geometry, while later peaks encode information about how matter clumped together in those early moments. Perhaps most astonishing is how delicate this balance was. If those primordial fluctuations had been even slightly smaller, gravity wouldn't have had enough to work with, leaving the universe a dark, featureless void. Too large, and matter would have collapsed into black holes before stars could form. Instead, we live in a Goldilocks cosmos, one where those 1 part in 100,000 variations were exactly right to build a universe rich with structure, yet stable enough to last billions of years. And here's the kicker: we're not just talking about ancient history. Those same fluctuations are still shaping the universe today. Every galaxy, every star, even the vast filaments of the cosmic web trace their origins back to those faint temperature differences in the CMB. So when astronomers map the microwave background, they're not just studying relics, they're reading the first draft of a story that's still being written, one where the faintest whispers from the dawn of time became the blueprint for everything we know. The cosmic microwave background isn't just a relic. It's a treasure trove of data, a celestial encyclopedia that cosmologists have spent decades decoding. Unlike distant galaxies or exploding stars, which only offer glimpses of specific places and times, the CMB is everywhere, carrying information about the entire universe in its faint glow. Think of it like finding an ancient manuscript that doesn't just describe one event, but the entire history of a civilization, its origins, its structure, even its eventual decline. That's the power the CMB holds. It doesn't just tell us where things are in the cosmos, it tells us why they're there, how they got there, and what might happen to them billions of years from now. One of its greatest gifts is how it reveals the universe's ingredients. By analyzing the CMB's fluctuations, scientists can calculate the exact proportions of ordinary matter, dark matter, and dark energy with precision that would have been unimaginable a century ago. It's like reverse engineering a recipe by tasting the final dish, except in this case, the dish is the entire observable universe. The CMB tells us that ordinary matter, the stuff of planets, stars, and people, makes up less than 5% of the cosmos. Dark matter, which we can't see but whose gravity shapes galaxies, accounts for about 27%. The rest, dark energy, the mysterious force accelerating the universe's expansion. Without the CMB, we might still be arguing over these numbers. Instead, they're etched into the sky, as undeniable as they are humbling, but the CMB's value goes beyond mere accounting. It's also a time-lapse camera, showing us how the universe evolved from a hot, dense plasma to the structured cosmos we see today. Those tiny temperature ripples didn't just predict where galaxies would form, they also reveal when they formed. By comparing the CMB's patterns with computer simulations, cosmologists can trace the growth of cosmic structure, watching virtual universes evolve in ways that eerily match our own. It's like having a billion-year-old weather forecast that turned out to be perfectly accurate. Perhaps most astonishing is how the CMB hints at the universe's ultimate fate. The same data that confirmed dark energy's existence also suggests it's growing stronger, meaning the cosmos might keep expanding faster and faster until galaxies are torn apart, stars fade, and space itself becomes a cold, empty void. The CMB doesn't just show us where we've been, it's a warning light on the cosmic dashboard, hinting at a future so distant it's hard to fathom. Yet for all its revelations, the CMB still holds mysteries. Why is the universe's expansion accelerating? What is dark energy? Are there hidden dimensions or parallel universes imprinting subtle anomalies we haven't detected yet? Every answer the CMB provides seems to spawn new questions, keeping cosmologists glued to their telescopes, searching for clues in microwave static older than time itself. That's the true magic of this ancient light. It's not just a snapshot of the past. It's a puzzle box, a mirror, and a crystal ball all at once, offering glimpses of realities we're only beginning to understand. Among the most tantalizing possibilities hidden in the cosmic microwave background is something straight out of science fiction: the potential fingerprints of other universes. According to some bold theories, certain anomalies in the CMB's patterns might not just be random quirks, but evidence of collisions with parallel universes in a vast multiverse. Imagine our cosmos as one bubble in a frothing sea of universes, each with its own physics, its own laws, occasionally brushing against others, and leaving faint scars in the oldest light we can see. The idea hinges on an extraordinary concept called eternal inflation, which suggests our universe is just one of countless bubble universes, constantly budding off an endlessly expanding spacetime foam. If two such bubbles ever grazed each other in the early epochs of cosmic history, the energy released could have imprinted a distinct signature on the CMB, a kind of cosmic bruise. Scientists have speculated these marks might appear as unusual circular patterns in the microwave background, regions where temperature fluctuations don't match the otherwise random distribution. One of the most discussed candidates for such an anomaly is the so-called cold spot, a strangely large and cool region in the CMB that defies easy explanation. While conventional physics might attribute it to statistical chance or foreground interference, some researchers propose it could be the shadow of a long-ago collision with another universe. Picture two soap bubbles gently pressing together. The spot where they meet would stretch and distort, leaving a telltale warping at the edges. If a parallel universe had brushed against ours, the gravitational energy of that encounter might have siphoned heat away from that patch of sky, leaving it colder than its surroundings. Of course, this isn't the only interpretation. Skeptics argue the cold spot could simply be a vast cosmic void, a region where matter is unusually sparse, stretching the light passing through it and cooling the CMB in that direction. Others suggest instrumental glitches or statistical flukes, but the multiverse hypothesis remains compelling because it offers a testable prediction. If bubble collisions are real, there should be multiple such imprints in the CMB, each with specific geometric signatures. Future telescopes with even finer resolution might one day spot these ghostly handshakes between universes, or rule them out entirely. What makes this idea so electrifying isn't just the possibility of parallel worlds, but the way it turns the CMB into a detective's notebook for the multiverse. Those subtle temperature variations we've mapped so meticulously might contain more than just the history of our universe. They could be a palimpsest layered with whispers from realities beyond our own. And if that's true, then the cosmic microwave background isn't just a relic of our past. It's a window into a cosmos vaster and stranger than we ever dared to dream. The cosmic microwave background won't shine forever. It's slowly fading into the cosmic static, a victim of the universe's relentless expansion. Right now, that ancient glow sits at a chilly 2.7 Kelvin, but in the distant future, it won't just get colder, it will vanish from detectability entirely. This isn't some sudden disappearance, it's a gradual fading like the last embers of a fire cooling to black, stretched over time scales so vast they dwarf human history. Here's what's happening. As space expands, it stretches the CMB's light waves, shifting them from microwaves to longer, lower energy wavelengths. Think of it like drawing a wave on a rubber band. Stretch the band, and the peaks and valleys grow farther apart. That's redshift in action. Over billions of years, the CMB's already faint microwaves will stretch into radio waves, then infrared, their energy dissipating until they blend into the cold, empty background of space itself. But the real kicker, the expansion isn't just stretching light, it's accelerating. Dark energy, the mysterious force pushing galaxies apart faster and faster, ensures that the CMB's journey toward invisibility isn't linear but exponential. In roughly 100 billion years, the CMB's redshift will be so extreme that its wavelength will exceed the size of the observable universe. At that point, the photons' once vibrant light from the dawn of time will have stretched into undetectability, their energy spread so thin that no instrument could ever tease them out from the cosmic noise. This has eerie implications. Future civilizations, if any exist, won't have the CMB as a guide. To them, the universe won't bear any obvious traces of the Big Bang. The night sky will appear vastly different, with galaxies beyond our local group redshifted out of view, leaving only darkness punctuated by a handful of nearby stars. Without the CMB's clues, piecing together cosmic history will be nearly impossible. We live in a privileged era, cosmically speaking. A brief window when the universe's oldest light is still just barely detectable, offering answers to questions future astronomers might never think to ask. Yet there's a strange beauty to this fading. The CMB's gradual disappearance mirrors the universe's own fate, an inexorable slide toward cold, empty expansion. Just as the afterglow of creation dims, so too will the stars, the galaxies, even the black holes, until the cosmos is a vast, silent graveyard of diluted particles. For now, though, we're here to listen to the whispers of that ancient light, to decode its stories before they slip away forever. It's a reminder that knowledge, like the universe itself, is fleeting, and that makes every discovery we pull from this fading glow all the more precious. Before the cosmic microwave background was discovered, cosmology was a battleground of competing theories. Some scientists believed in a steady-state universe, eternal and unchanging. Others argued for a fiery beginning, the Big Bang, but lacked definitive proof. Then, in 1965, everything changed when Penzias and Wilson stumbled upon that faint microwave hum. That accidental discovery didn't just settle the debate. It rewrote the rules of cosmic history, turning cosmology from speculation into precision science. What made the CMB so revolutionary was its irrefutable clarity. Here was a signal that matched Big Bang predictions with near-perfect accuracy, a uniform glow left over from a time when the universe was unimaginably hot and dense. Before this, the Big Bang was just one idea among many, Afterward, it became the cornerstone of modern cosmology. The CMB was like finding the Rosetta Stone of the cosmos, a key that unlocked our ability to read the universe's earliest chapters. Suddenly, scientists had a time machine. By analyzing this ancient light, they could test theories about the universe's composition, its age, even its ultimate fate. The CMB revealed that ordinary matter, the stuff of stars and planets, makes up less than 5% of everything. It hinted at the existence of dark matter decades before direct observations. Later, it would help uncover dark energy's role in accelerating cosmic expansion. Each revelation was like peeling back another layer of the universe's deepest secrets, all thanks to that faint microwave whisper. But the impact went beyond evidence. The CMB gave cosmology a new language, mathematics. Before, grand cosmic theories were often philosophical. After, they became quantifiable. Those tiny temperature fluctuations weren't just patterns. They were equations written across the sky, solvable with physics and probability. This shift didn't just validate the Big Bang, it transformed cosmology into a hard science as rigorous as particle physics or chemistry. Perhaps most profoundly, the CMB reshaped humanity's place in the cosmic story. For centuries, we saw the universe as static, eternal. The CMB showed us it had a birthday, a definite beginning. That realization echoed beyond labs and lecture halls, influencing philosophy, religion, even art. It's one thing to theorize about creation. It's another to hold a photograph of it, to measure its temperature, to map its imperfections. The CMB didn't just change science, it changed how we see ourselves in the grand sweep of time and space. And the revolution isn't over. Every new generation of telescopes, from Kelvin to Planck, has extracted deeper truths from this ancient light. Today, as we hunt for primordial gravitational waves in the CMB's polarization, we're chasing clues about the universe's first trillionth of a second. That's the CMB's enduring power. It's not just a relic of the past, but a bridge to discoveries we haven't even imagined yet. What began as an annoying hum in a radio antenna became the foundation for everything we know about the cosmos and the key to everything we still don't. To truly grasp the cosmic microwave background's secrets, we had to leave Earth behind because our atmosphere blurs and scatters these ancient microwaves like ripples on a windy pond. That's why some of humanity's most ambitious telescopes aren't perched on mountaintops, but orbiting high above our planet, where they can study the CMB's pristine signal without atmospheric interference. The first of these cosmic cartographers was NASA COBE satellite, launched in 1989. Imagine trying to photograph a candle's flicker from miles away. That's the level of precision COBE achieved when it made the first full sky map of the CMB's temperature variations. Its instruments were so sensitive they could detect differences of just 1 part in 100,000, revealing the universe's primordial wrinkles for the very first time. COBE findings were so groundbreaking that its lead scientists won the Nobel Prize, proving the Big Bang theory beyond reasonable doubt, but COBE was just the beginning. In 2001, NASA Wilkinson Microwave Anisotropy Probe WMAP took the baton, mapping the CMB with nearly 40 times COBE resolution. WMAP didn't just confirm the universe's age as 13.7 billion years, it precisely measured the percentages of dark matter and dark energy for the first time, reshaping our understanding of cosmic composition. Its data revealed the exact moment when the first stars ignited about 400 million years after the Big Bang, and even hinted at cosmic inflation's fingerprints. WMAP all sky maps look like celestial fingerprints, swirling with intricate patterns that held clues to the universe's birth, growth, and ultimate fate. Then came Planck, launched by the European Space Agency in 2009. This marvel of engineering was the most advanced CMB observatory ever built. Planck's detectors were so sensitive they could spot temperature variations smaller than a millionth of a degree, like discerning a single warm grain of sand on an Antarctic ice sheet. Over 4 years, Planck mapped the CMB's polarization in unprecedented detail, uncovering subtle patterns that may hint at primordial gravitational waves. Its data refined the universe's age to 13.8 billion years and revealed the cosmos is expanding slightly slower than we thought, a tiny number with massive implications. What's astonishing is how each mission built on the last, like archaeologists brushing dust from an ancient artifact to reveal finer details. Decode showed us the CMB's large-scale features, WMAP sharpened the image, and Planck brought it into ultra-high definition. These telescopes didn't just confirm theories, they exposed gaps in our knowledge, like the mysterious axis of evil, an unexpected alignment in the CMB's fluctuations that still puzzles cosmologists. Now, next-generation telescopes like the Simons Observatory and Lightbird are pushing even further, hunting for B-mode polarization patterns that could prove cosmic inflation occurred. They're the cosmic equivalent of upgrading from a flip phone to a smartphone, with detectors so precise they could spot a microwave glow from a single snowflake on Pluto. Every new mission peels back another layer of this ancient light, revealing secrets we haven't even thought to ask about because sometimes the universe's answers come long before we learn the right questions. If you've ever pressed your finger onto an ink pad and left a print behind, you've created something eerily similar to the cosmic microwave background, a one-of-a-kind mark that tells a story no other can replicate. Those delicate swirls and ridges in your fingerprint aren't just random, they're a blueprint of who you are, shaped by genetics and chance. The CMB's temperature fluctuations work the same way. They're the universe's unique signature, a coded message about how everything began, written in the language of microwaves. Take a close look at a high-resolution map of the CMB, and you'll see a mottled pattern of warmer and cooler spots like the dappled light beneath a tree. These aren't arbitrary. Each variation, no matter how slight, encodes critical details about the universe's ingredients and structure. It's as if the cosmos pressed its fiery, newborn hand onto the fabric of space-time, leaving behind an imprint we're still deciphering. The hotter patches, they trace where matter was slightly denser in the early universe. The cooler regions, hints of where gravity had less to work with, eventual homes for today's vast cosmic voids. What makes this cosmic fingerprint so powerful is its specificity. Just as no two people share identical fingerprints, no other universe, if others exist, would have a CMB exactly like ours. The precise arrangement of those fluctuations depends on countless variables. The exact mix of matter and energy, the rate of cosmic expansion, even quantum quirks from the first instance after the Big Bang. Change one parameter, even slightly, and the entire pattern shifts. That's why scientists treat the CMB like a forensic clue, using its ridges and walls to reconstruct the universe's earliest moments with shocking accuracy. Here's the staggering part. We've learned to read this fingerprint well enough to extract numbers as precise as the universe's age, 13.8 billion years, give or take 40 million. We've weighed the amount of dark matter, measured dark energy's push, even deduced the curvature of space itself, all from subtle variations in microwave static. It's like deducing someone's entire life story, their birthplace, their diet, their ancestry from a single smudged thumbprint. But the most beautiful parallel lies in what fingerprints and the CMB both represent: uniqueness born from chaos. Your fingerprints formed from random stresses in the womb, their patterns unpredictable yet deeply personal. The CMB's fluctuations arose from quantum noise, microscopic randomness inflated to cosmic scales. Yet both became enduring identifiers, carrying stories of origin that nothing else can tell. The universe could have been smooth, featureless, but instead, it left us this intricate, imperfect mark, a testament to the beautiful disorder that made everything we know possible. And just like detectives who lift prints from surfaces invisible to the naked eye, cosmologists are still developing new ways to uncover the CMB's hidden details. Future telescopes might reveal even finer patterns, like the microscopic sweat pours along a fingerprint's ridges, offering clues to mysteries we haven't even named yet. The CMB isn't just a fossil, it's a living document, one we're only beginning to decode. And as we do, we're learning that every subtle wrinkle in this ancient light is part of a story far grander than we ever imagined. The cosmic microwave background doesn't just confirm our theories, it tears holes in them, revealing gaps in our understanding so profound they've sparked a crisis in modern cosmology. Take the Hubble tension, a puzzle so stubborn it's divided astronomers into rival camps. On one side, we have the CMB's pristine measurements, suggesting the universe expands at 67 kilometers per second per megaparsec. On the other, observations of nearby galaxies and supernova insist it's 73, a discrepancy that sounds trivial until you realize these numbers anchor everything we know about cosmic history. It's like two clocks, both impeccably crafted, ticking at irreconcilable speeds. The CMB's data comes from a time when the universe was a mere 380,000 years old, while local measurements reflect the cosmos today. Either we're misreading one of these cosmic yardsticks, or something fundamental: dark energy's behavior, gravity's rules, even the nature of space-time itself, isn't what we thought. This isn't just academic quibbling. The Hubble tension threatens to upend our most cherished models. If the CMB's expansion rate is correct, then distant supernova should appear dimmer than they do. Yet they shine too bright, as if space isn't stretching as fast as our theories predict. Some propose dark energy evolves over time, growing stronger or weaker in ways we haven't accounted for. Others whisper about new physics, exotic particles, extra dimensions, or modifications to Einstein's relativity that only manifest across cosmic scales. The most radical suggestion that we're seeing echoes of a pre-Big Bang era, artifacts from a previous cycle of the universe imprinted in the CMB's anomalies. Then there's the CMB's own quirks, like the unsettlingly low variance in temperature fluctuations at large scales. It's as if someone took a pair of cosmic scissors and snipped off the most extreme highs and lows, leaving the universe suspiciously smooth. Add to that the axis of evil, an alignment of hot and cold spots that defies the assumption the cosmos should look the same in all directions, and you've got a recipe for scientific sleepless nights. These aren't mere statistical flukes, they're potential cracks in the foundation of our cosmic worldview, hints that the universe might be far stranger than our equations can describe. What makes these puzzles so exhilarating is how they mirror past revolutions in physics. A century ago, the ultraviolet catastrophe and Mercury's erratic orbit exposed flaws in classical theories, paving the way for quantum mechanics and relativity. Today, the CMB plays a similar role, its anomalies acting as breadcrumbs leading us toward deeper truths. Every discrepancy is an invitation, a chance to rewrite the textbooks, or perhaps to realize we've been reading them wrong all along. The cosmic microwave background isn't just a relic of the past, it's a mirror reflecting not only how far we've come, but how much further we have to go. At the heart of modern physics lies a paradox so profound it's kept scientists awake for decades: quantum mechanics and general relativity. Our two most successful theories of reality refuse to speak the same language. One governs the subatomic world with probabilities and uncertainties, while the other sculpts the cosmos with the smooth curves of spacetime. Yet where they should meet, in the violent infancy of the universe or the crushing depths of black holes, their equations explode into nonsense. That's where the cosmic microwave background might offer an unexpected bridge. Hidden in the CMB's faint whispers could be the faintest traces of quantum gravity, a theory that would unite these warring frameworks into a single, elegant description of nature. The key lies in the universe's first trillionth of a second, when everything was so small and dense that quantum fluctuations didn't just affect particles, they warped spacetime itself. According to some theories, these spacetime tremors left scars on the cosmos, imprinted in the CMB's polarization patterns like footprints in wet concrete. One tantalizing possibility involves primordial gravitational waves. During cosmic inflation, the universe's explosive growth spurred quantum jitters in the fabric of spacetime may have been stretched to cosmic scales, creating ripples that still ripple through the cosmos today. These wouldn't be ordinary gravitational waves like those from colliding black holes. They'd be fossils from an era when gravity itself behaved quantum mechanically. Detecting their signature in the CMB's B-mode polarization would be like finding a letter from the universe's first moments, written in the language of quantum gravity. But the clues might be subtler. Some models suggest the CMB's temperature fluctuations could show anomalies, strange statistical quirks, or unexpected alignments that hint at spacetime's granular structure at the smallest scales. Imagine zooming in on a seemingly smooth photograph until you see the pixel grid. Quantum gravity predicts a similar pixelation of spacetime, and its echoes might linger in how the CMB's patterns distribute across the sky. What makes this search so electrifying is its stakes. If the CMB reveals even a whisper of quantum gravity, it wouldn't just solve a theoretical puzzle, it'd rewrite our understanding of reality's fundamental building blocks. Are there hidden dimensions curled up smaller than atoms? Does spacetime emerge from deeper, more primitive ingredients? The CMB might not answer these questions directly, but like a cosmic Rosetta Stone, it could give us the first critical hints. Of course, the challenges are staggering. These signals, if they exist, are buried under layers of cosmic noise, drowned out by interstellar dust and the hum of more mundane physics. It's like trying to hear a single instrument in a symphony playing at the edge of the universe, yet with telescopes growing ever more sensitive, like the upcoming Lightbird mission, designed to hunt for these very fingerprints. We're closer than ever to tuning into frequencies that might carry the universe's deepest secrets. The irony is delicious. Quantum gravity deals with the smallest conceivable scales, while the CMB spans the largest. Yet in that contrast lies the genius of using this ancient light as a probe. The universe's oldest snapshot might just hold the key to its smallest workings, a reminder that sometimes to see the tiniest details, you need the grandest possible lens. The cosmic microwave background doesn't just show us the universe at 380,000 years old. It might be our only window into the very first fraction of a second after the Big Bang, a period so unimaginably brief and extreme that even our best physics breaks down. This era, known as the Planck epoch, lasted a mere 10 to the power of -43 seconds, a timescale so short it makes a blink feel like an eternity. During this fleeting moment, the entire cosmos was compressed into a space smaller than an atom, with temperatures and densities so extreme that gravity itself behaved as a quantum force. Under these conditions, spacetime wasn't the smooth, predictable fabric we know today. It was a seething, frothing foam where distances and durations fluctuated wildly, and the very concepts of before and after lose meaning. Here's the astonishing part. Even though we can't observe this epoch directly, the CMB's imperfections might carry echoes of its chaos. Those tiny temperature fluctuations, the ones that seeded galaxies, aren't just random noise. They could be magnified relics of quantum jitters from the Planck epoch, stretched to cosmic proportions during inflation. Picture a microscope zooming in on a grain of sand to reveal scratches left by colliding atoms, except in this case, the scratches are imprinted across the entire sky, frozen in microwaves. Some theories suggest these primordial quantum fluctuations were the universe's first act of creation, microscopic ripples in spacetime that inflation ballooned into the vast cosmic structures we see today. If true, the CMB isn't just a snapshot, it's a palimpsest layered with whispers from an era when time and space themselves were still taking shape, but the clues might be even stranger. Certain anomalies in the CMB, like the elusive B-mode polarization patterns, could hint at gravitational waves generated during the Planck epoch, waves strong enough to ripple through the infant universe and leave their mark on its oldest light. Detecting these would be like finding a fossilized vibration from the moment gravity itself was born. Of course, we're not just guessing. The Planck satellite's painstaking measurements have already ruled out some theories of quantum gravity while leaving others tantalizingly plausible. Future telescopes with even finer precision might spot the telltale swirls of primordial gravitational waves, confirming that the universe's first moments were even wilder than we've dared to imagine. What's humbling is how much we still don't know. The Planck epoch exists at energies a quadrillion times beyond what particle colliders can reach, in a realm where our current laws of physics dissolve into uncertainty. Yet somehow, through the CMB's faint glow, we're piecing together a story written in the universe's first quantum whispers, a story where every fluctuation, every anomaly, is a breadcrumb leading us closer to the ultimate question: what sparked existence itself? And the most thrilling part, we're only just beginning to read it. Every photon of the cosmic microwave background reaching our telescopes today has been on an odyssey longer than any epoch in human history, a 13.8 billion-year voyage across an ever-expanding cosmos. These ancient particles of light didn't just traverse unimaginable distances, they witnessed the universe's grand transformation from a scorching plasma to the star-studded expanse we inhabit now. Picture a single photon born in the chaos of recombination, finally striking a detector on Earth after a journey so vast it makes the lifespan of galaxies seem fleeting. When these photons began their journey, the universe was a mere 380,000 years old, a cosmic toddler. Space was so dense that atoms couldn't even form without being instantly torn apart. But as the cosmos expanded and cooled, that searing plasma finally thinned enough for light to break free, creating the first sunrise in existence. That initial burst of light, what we now call the CMB, wasn't initially microwaves. It blazed forth as visible light, even ultraviolet, glowing white-hot like the surface of a star. But the universe had other plans. As space stretched over eons, so did the light itself. The same expansion that carried galaxies apart also lengthened the photons' wavelengths, redshifting them from visible light into infrared, then microwaves, and eventually, given enough time, into radio waves so faint they'll one day fade beyond detection. This relentless stretching is why the CMB now appears as a feeble microwave whisper, barely a few degrees above absolute zero. Those photons didn't lose energy, they've been stretched thin by the expanding fabric of space itself, like ink on a balloon's surface spreading as it inflates. But here's the mind-bending part: those photons didn't travel in a straight line. The universe isn't static, it's been stretching beneath the CMB's light for billions of years. The distance those photons covered when they started their journey was a mere fraction of where they'd end up. It's like a marathon runner racing on a track that keeps elongating, turning every step into a greater challenge. By the time the CMB reaches us, the space it crossed has expanded so much that the original distance, what cosmologists call the proper distance, has grown to an astonishing 46 billion light-years. And the journey wasn't peaceful. Along the way, these photons interacted with the universe's evolving structure. Some passed through galaxy clusters so massive they bent the light's path like a lens, subtly distorting the CMB's patterns, an effect called the Sunyaev-Zeldovich effect. Others were subtly shifted in energy by encounters with electrons in the cosmic web, leaving faint imprints that reveal where matter clumps today. These aren't just relics of the past, they're messengers carrying stories from every era they've traversed. What's humbling is realizing how much of this light we're missing. The CMB we detect is just the tiny fraction that happened to intersect Earth after billions of years. Countless other photons are still streaming through the void, forever unseen, while others have already redshifted beyond recognition. our ability to catch even a whisper of this ancient light is a fleeting cosmic privilege, one that won't last forever. In another trillion years, the CMB will have faded entirely, leaving future civilizations with no trace of the universe's fiery birth. So when you look at a CMB map, remember, you're not just seeing static. You're witnessing the final moments of a 13 billion-year journey, the last whispers of light from a time when the cosmos was young enough to fit in the palm of reality's hand. And every photon tells a story if we're patient enough to listen. The cosmic microwave background is more than a relic, it's a cosmic speedometer, revealing how fast the universe has been stretching since its earliest moments. At the heart of this measurement lies the Hubble constant, a deceptively simple number representing how many kilometers per second a galaxy moves away from us for every megaparsec of distance. But pinning down this value has sparked one of modern cosmology's greatest debates, and the CMB holds critical clues to resolving it. Here's how it works. When we map the CMB's temperature fluctuations, we're essentially measuring the acoustic peaks, the frozen ripples of those primordial sound waves that traveled through the early universe's plasma. The spacing between these peaks acts like a cosmic ruler, revealing how far those sound waves could travel before recombination. Since we know the speed of sound in that primordial soup, we can calculate the universe's expansion history with astonishing precision. It's like finding an ancient musical instrument and deducing the size of the room it was played in by analyzing its echoes. But there's a catch. The CMB doesn't measure today's expansion rate directly. It provides a starting point that must be combined with our understanding of dark energy and matter to extrapolate forward 13.8 billion years. This cosmological inverse problem gives us a Hubble constant of about 67 kilometers per second per megaparsec, a number that should, in theory, match what we measure by observing nearby galaxies and supernova. Except it doesn't. Those local measurements consistently land around 73, creating what scientists call the Hubble tension. This discrepancy isn't just academic quibbling. If the CMB's derived expansion rate is correct, it implies our models of dark energy or galaxy formation might need overhauling. Maybe dark energy's strength has changed over time, or perhaps undiscovered particles altered the early universe's sound speed. Some physicists even speculate about cracks in Einstein's gravity theory itself. The CMB becomes both referee and provocateur in this debate. Its pristine measurements are so precise that any mismatch forces us to question our fundamental assumptions about cosmic evolution. What's remarkable is how this ancient light serves as the ultimate calibration tool. While local methods measure expansion using standard candles like Cepheid variables or Type Ia supernova, each with their own potential biases, the CMB offers an independent check rooted in different physics entirely. It's like verifying your bathroom scale by also weighing yourself on a balance beam. If they disagree, something's wrong with at least one method. The CMB's consistency with other probes, like baryon acoustic oscillations in galaxy surveys, only deepens the mystery of why local measurements diverge. Recent advances have made this puzzle even more intriguing. The Atacama Cosmology Telescope and South Pole Telescope have measured the CMB's subtle distortions caused by intervening galaxy clusters, providing yet another path to the Hubble constant. Their results smack in between the local and early universe values, further muddying the waters. This isn't just about numbers, it's a potential window into physics beyond our standard models, a whisper that the universe might be more complex than our equations can yet describe. The stakes couldn't be higher. The Hubble constant doesn't just tell us how fast space is stretching, it sets the cosmic timeline, determining the universe's age and ultimate fate. If we've misjudged it, even slightly, our entire story of cosmic evolution might need rewriting. And that's the CMB's greatest gift in this ongoing saga. It keeps us honest, providing an unflinching benchmark against which all other measurements must be tested. In the end, whether the tension resolves through better measurements or revolutionary physics, one thing's certain: this ancient light will continue guiding us toward deeper truths about the expanding cosmos we call home. What if the cosmic microwave background is hiding more than just the universe's ancient secrets? Some daring theories suggest those subtle temperature fluctuations might be whispering clues about realms beyond our own, hidden dimensions curled up so tightly we've never detected them. Imagine our universe as a loaf of bread, where every slice represents the three-dimensional space we know. But what if the loaf itself exists in a higher dimensional bulk, with parallel slices brushing against ours in ways that leave faint imprints on the CMB? This isn't science fiction, it's string theory's playground. In these models, extra dimensions could subtly alter gravity's behavior on cosmic scales, warping how those primordial sound waves propagated through the early universe. The result: odd asymmetries or unexpected patterns in the CMB's fluctuations, like finding fingerprints on a window that no one in the room could have left. One tantalizing hint comes from the CMB's large-scale anomalies, like the axis of evil, an apparent alignment of hot and cold spots that defies standard cosmology. Could these be gravitational echoes from dimensions we can't see, crumpled like origami at scales smaller than an atom? The math gets wilder. Some theories propose that colliding branes, higher dimensional membranes, in this hidden bulk space could have triggered our Big Bang, leaving behind telltale signatures in the CMB's polarization. Others suggest that quantum fluctuations in higher dimensions might have leaked into our 3D universe during inflation, imprinting distinctive swirls in the microwave background. Detecting these would be like finding a bullet hole in a photograph and realizing the shot came from outside the frame. Of course, the challenge is separating cosmic coincidence from genuine evidence. The Planck satellite's painstaking measurements have ruled out some exotic dimension models, while others remain tantalizingly plausible. Future telescopes hunting for primordial gravitational waves might catch these dimensional whispers more clearly if they exist. It's a long shot, but the payoff would rewrite physics. After all, the CMB has surprised us before. Who's to say it won't do so again by revealing that reality is far roomier than we ever dreamed? There's something humbling about realizing the cosmic microwave background isn't just an abstract scientific curiosity, it's a direct thread connecting each of us to the universe's fiery beginnings. Every time we detect this ancient light, we're not just collecting data, we're touching a remnant from a time before time, a moment when everything we know, every star, every planet, every living thing existed only as potential written in the faintest temperature fluctuations. This glow is more than radiation. It's a shared heritage, a whisper from the cosmos reminding us that the atoms in our bodies were forged in the same primordial crucible that birthed galaxies. Think about what that means for a moment. The photons hitting a telescope's sensor today began their journey 13.8 billion years ago, when the universe was a mere 380,000 years old. In that time, they've witnessed the rise of the first stars, the assembly of galaxies, the birth and death of countless suns, all while racing through an ever-expanding cosmos, only to land here now in our instruments. It's as if the universe left a message in a bottle, drifting across eternity just for us to find, and in decoding it, we're not just passive observers. We're participants in a story that began before our planet, our solar system, even the Milky Way existed. This connection transcends science, it's deeply human. For millennia, cultures have looked to the sky for meaning, weaving myths about creation and our place within it. The CMB offers a modern answer to those ancient questions, not in poetry but in precise, measurable light. Those subtle temperature variations, they're the reason we're here. Without them, matter would have remained evenly distributed, gravity would have had nothing to grasp, and the universe would be a vast, featureless void. Instead, those tiny wrinkles became the seeds of structure, the scaffolding for everything from galaxy clusters to the DNA in your cells. You're not just looking at the CMB, you're a product of it. There's a quiet awe in that realization. The same processes that carved the cosmos also shaped us, linking our existence to the grandest scales of space and time. When astronomers map the CMB's fluctuations, they're not just charting the past, they're tracing the origins of the very elements that make life possible. The carbon in your bones, the oxygen in your breath, the iron in your blood, all were forged in stars that formed because of those primordial density variations. The universe didn't just create us, it left a receipt, a way to trace our lineage back to the beginning. And here's the most beautiful part: this connection isn't one way. By studying the CMB, we're not just receiving a message from the past, we're sending one to the future. Every observation, every breakthrough adds to humanity's collective understanding, a legacy that will outlast us. Long after our telescopes turn to dust, the CMB will still be there, a silent witness to the universe's unfolding story. For now, though, we're here to listen, to learn, and to marvel at the profound truth that we're not just in the universe, we're of it, woven into its fabric as surely as the oldest light in the sky. The cosmic microwave background is more than just a relic of the past, it's a living foundation for the future of cosmology. Long after today's telescopes fall silent and the cutting-edge theories of our era become textbook footnotes, the CMB will still be there, whispering its secrets to generations of scientists we can't yet imagine. This ancient light isn't merely a snapshot frozen in time. It's an evergreen tool, one that will continue reshaping our understanding of the universe as technology advances and new questions emerge. Consider how far we've come since Penzias and Wilson first puzzled over that mysterious static in 1965. Back then, the CMB was a curiosity, an unexplained signal cluttering radio antennas. Today, it's the backbone of modern cosmology, the yardstick against which we measure everything from the universe's age to the nature of dark energy. And this is just the beginning. Future observatories, like the proposed CMB S4 project, will map this radiation with resolutions 100 times sharper than Planck's, uncovering details we can't even conceive of yet. These next-generation telescopes won't just refine existing theories, they'll likely expose gaps in our knowledge so profound they'll spark entirely new branches of physics. What makes the CMB uniquely enduring is its universality. Unlike distant galaxies or transient supernova, which offer glimpses of specific places and times, the microwave background is everywhere, encoding information about the cosmos as a whole. It's both a time capsule and a Rosetta Stone, preserving data about the universe's infancy while providing the key to decode it. Even as astrophysics pivots to study gravitational waves, neutrino astronomy, and other emerging fields, the CMB will remain the gold standard for testing big ideas, from quantum gravity to the multiverse. Its patterns are a cosmic control group, an unchanging reference point against which all other observations must be weighed. But the CMB's legacy extends beyond pure science. It represents something deeply human, our relentless drive to understand where we came from. For thousands of years, cultures have told creation stories, weaving myths to explain the origins of everything. The CMB offers something no myth ever could: a direct, measurable connection to the universe's birth, one that transcends language and culture. It's a reminder that the same physical laws that shaped galaxies also shaped us, linking our fleeting existence to the grandest scales of time and space. Perhaps most remarkably, the CMB's story isn't static. As experimental techniques evolve, we'll extract new layers of meaning from this ancient light, much like historians rereading a familiar text with fresh eyes. The anomalies puzzling us today, the cold spot, the axis of evil, might one day seem obvious clues pointing toward truths we can't yet grasp. And when future breakthroughs rewrite cosmology's rulebook, the CMB will be there, ready to test those ideas with the same impartial clarity it's always offered. So while stars will burn out and galaxies will drift apart, this faint microwave glow will persist, carrying its message across the eons. It's a testament to the universe's ingenuity that something as simple as cooled light could hold the blueprint for everything. And as long as there are curious minds to listen, the CMB will keep speaking, revealing not just how the cosmos began, but how much we still have left to discover. From the moment it was accidentally discovered as stubborn radio static to its current status as cosmology's most revealing artifact, the cosmic microwave background has rewritten our understanding of existence itself. Over 30 astonishing facts, we've explored how this ancient glow serves as a time machine, a blueprint, and even a cosmic controversy starter. It's the afterglow of the Big Bang, yes, but also so much more. A fossilized echo of quantum ripples stretched across the universe, a snapshot of spacetime's curvature, and a cryptic message hinting at realms beyond our own. Think about what this means. Those faint microwaves filling every cubic inch of space tell us the universe is 13.8 billion years old, and that less than 5% of it is made from the stuff we can see. They whisper about dark matter's invisible scaffolding and dark energy's relentless push, forces so mysterious they make up 95% of reality yet evade direct detection. The CMB's delicate temperature variations, smaller than 1 part in 100,000, became the gravitational seeds for galaxies, stars, and ultimately, us. Without those microscopic imperfections, the cosmos would be a featureless void, no planets, no life, just endless sameness, but the revelations go deeper. This primordial light carries echoes of the universe's first sound waves, frozen ripples from a time when space itself rang like a bell. It exposes anomalies that challenge our best theories, from the eerie smoothness of the early cosmos to the controversial axis of evil alignment. Some researchers even scour its patterns for fingerprints of other universes, potential evidence that our cosmos is just one bubble in an infinite multiverse. Every new observation peels back another layer, revealing questions we haven't even thought to ask yet. Here's what's truly breathtaking: the CMB isn't some distant phenomenon. It's all around you right now, that static on an old television. About 1% of it was the universe's birth cry, those microwaves penetrating your walls as you watch this video. They've traveled 13 billion years to reach you, unchanged except for the stretching of space itself. You're literally bathing in the oldest light in existence, a glow older than every star, every planet, every mountain or ocean Earth has ever known. So as we wrap up this journey through cosmic history, I want to leave you with a question, not just about the universe's origins, but about our place within it. Every discovery in cosmology chips away at the illusion of separateness, reminding us that we're not just observers of the cosmos, but participants in its story. The atoms in your body were forged in stars born from those primordial density fluctuations. The air you breathe, the device you're watching this on, even the electricity powering it, all trace back to cosmic processes imprinted in the CMB's patterns. What mysteries do you think remain hidden in this ancient light? Could future telescopes uncover evidence of pre-Big Bang physics, or even signs of other dimensions? Drop your wildest theories in the comments, because the beauty of cosmology is that it's never finished. The CMB has been speaking for 13.8 billion years, and we're only just learning to listen. Who knows what secrets it will whisper next?